This conference will now be recorded.
Hello everyone. The topics that we are going to discuss today is coordination bond or dative bond. That is, any of these names are fine for this type of bond. Then hydrogen bond, bonding, bond order, bond enthalpy, bond angle, and there will be some related problems. So here we have the first problem. Variable covalency is exhibited by. So last day we have already seen what is variable covalency, what is the definition. We also have seen some examples. Now we have to solve this problem, which is based on variable covalency. Here we have options: phosphorus and sulfur, nitrogen and oxygen, nitrogen and phosphorus, and fluorine and chlorine. Now we have already seen that variable covalency is possible only when it is at least not from second period, because when it is second period, if we consider any second period element, here we have nitrogen, oxygen, then fluorine. So these three elements, they are from second period. Now in second period we have only 2s and we have 2p. Okay, so 2s and 2p, only these two we have. Just take the example of nitrogen. Here outermost electronic configuration is 2s2 2p3. Now it can maximum use these 3 unpaired electrons for bond formation. So that is why here further change in any valency not possible, because the pair that you can see in 2s, this pair we cannot break and shift this electron to any d, because we do not have any d orbital. We just have 2s and 2p. We do not have any d orbital. So that is why transfer of electron not possible. And when transfer of electron not possible, that means we cannot have 5 unpaired electrons. We can have max 3 unpaired electrons. So that is why covalency will be only 3. It cannot be variable. So that is why variable covalency not possible if it is second period element. So same thing, same logic is also applicable for oxygen, for fluorine. But chlorine, phosphorus, sulfur, these 3 elements, they can show variable covalency, which is clear. So see, phosphorus, sulfur and chlorine, these 3 can show variable covalency, but we have to choose that option where both the elements, because in each option we have pair. That option you have to choose where both the elements can show variable covalence. So that is why the first option will be the correct option, because in the last option, option 4, though chlorine is correct, but chlorine is not correct. Okay. P and S, this is the correct option. Next question, what is covalency of chlorine in its second excited state? Now chlorine, it shows variable covalency that we have just seen in the previous problem. But in the second excited state, what will be its covalency? Because there are different types of covalency possible for chlorine. Okay, it is from third period. It is from group 17. That means valence electron is group 17. So valence electron is, you just have to consider the last digit of the group. Now it is 3s2. That means 2 electron will be present in 3s and 3p5. So 2 pair and 1 single electron. Okay. Now first excited state means you are breaking the first pair, and second excited state means now you are breaking the second pair. Okay. So if we see the orbital diagram of outermost electrons, here NS and NP is mentioned. Actually this pictorial representation, don't think it is for chlorine only, it is applicable for any halogen atom, because for any halogen atom group 17, whether you consider fluorine, chlorine, bromine, iodine, whatever, for all these elements this pictorial representation is possible. Sorry, not for fluorine, because for fluorine there is no d orbital, so it is only for Cl, Br and I. If it is Cl, n value is 3. If it is Br, it is 4s 4p 4d, and if it is iodine, it will be 5. Okay, so NS NP, it is NH2 NP5. Okay, so NH2 NP5, if this is the electronic configuration, when the first pair is broken, that is this electron is shifted. See in the second picture, now there is no pair and it is shifted to d orbital. So this is the first excited state. Okay. Now when it is second excited state, this is the first excited state, number 1. In the second excited state, now you are breaking the second pair also. So another electron is now present in Nd. So after the second excited state, now look at this picture. How many unpaired electrons are present? Total 5 unpaired electrons are present, 3 in Np, 2 in Nd. Basically for chlorine it is 3p and 3d. So 5 unpaired electrons are present. That means the covalency of chlorine in this second excited state will be 5. So correct answer is 5. Fine. So this is the answer, and also there is one more excited state is shown here, which is the third excited state. So suppose if the question is framed in such a way that what is the covalence of chlorine in this third excited state, then your answer will be, now you can see total 7 unpaired electrons are there because all the pairs are broken. So then the answer should be 7. So next we will see coordinate bond or dative bond. We already know what is ionic bond and what is covalent bond. So covalent bond, there is proper sharing of electron, and ionic bond is one atom is completely donating electron, another atom is completely accepting electron. So that is the difference. Now when it is coordinate or dative bond, this is a third type of bond, though this is not so common like covalent and ionic, but still we have to know this. So what is it, this type of bond? In some cases, what happens when there is bond formation, only one of the combining atoms is donating the pair of electrons that is necessary for bond formation. We know that what for bond formation, suppose we are having any bond between X element and Y element, and for bond formation, pair of electron necessary. That means 2 electrons will be there. Now in covalent bond, what you have seen, that one electron donated by X, another electron donated by Y. But in this case, the difference is both the electrons are donated by same element. So in this case, both these electrons are donated by X. That is the difference. Once it is donated, now these 2 electrons are shared equally between X and Y. Now the situation is just like covalent. But initially, both the electrons are donated by single atom. After that, it is behaving like covalent bond. Don't think there is any positive charge generation, negative charge generation, just in case of ionic bond. No, it is not like that. It is not ionic bond, it is not covalent bond, it is something else. So in certain cases during bond formation, only one of the combining atoms donates a pair of electrons that is necessary for bond formation, unlike covalent bond. So unlike covalent bond, why it is written? Because in covalent bond each atom is giving one electron, but in this case both the electrons are coming from single atom, and after that this pair of electrons are shared by both the atoms just as usual. So this is known as it is known in different names. Sometimes we call it coordinate bond or coordinate covalent bond or simply dative bond. Okay. So here you can see this reaction. Basically it is not a single compound. In this picture you can see there is reaction between ammonia and BF3. Okay. So in this why we have chosen a reaction, we can also choose a compound that we will also see example of a particular compound, but in this case there is reaction between NH3 and BF3, and you will see, we know there is a lone pair over nitrogen in ammonia, and BF3 is basically electron deficient compound. Remember when we have discussed octet rule, then some exception we have seen. And in exception, BF3 is one of the important example, because in BF3, boron is the central atom, but surrounding boron, there is total 3 valence electron. So boron is using all these 3 electrons for 3 bond formation. So surrounding boron, total number of electrons 6, which is lesser than 8. So it's octet, not complete. This molecule is electron deficient. So that is the reason now Now nitrogen is donating its electron pair to electron deficient boron, and once it is donated, now the bond between N and B formed, which is coordinate covalent bond, and this type of bond is shown, sometimes it is not shown by arrow, but sometimes it is shown by arrow, because here the direction of electron, it is from nitrogen towards boron, so that is why The arrow is towards boron. Okay, or you can write the molecule like this. So this is a bond formation between nitrogen and boron, which is coordinate bond. Okay. One more example we'll see. Water molecule. In water molecule, here first look at the water molecule itself. Oxygen has total 6 valence electron. Okay. Now out of these 6 valence electron, oxygen is using 1 electron for bond formation with this hydrogen, another electron for this one. And the cross mark that you are seeing here, that is actually the electron of hydrogen. So there is a bond between these two, and the 4 electrons that are remaining, still remaining there in the form of lone pair. Okay. Now in presence of H plus, what happens? H plus electron deficient, right? And oxygen has 2 lone pair. So this lone pair can be donated to H plus, and now there is a new bond formation between oxygen and this new hydrogen. Okay, so see, this is the newly generated bond where both the electrons that you are seeing here, because the electrons that are from oxygen, they are in dot sign, and the electrons that are from hydrogen, that is in cross sign. So this newly formed bond that I have just marked with red color, in this bond you can see both the electrons in dot sign. That means oxygen, these 4 electrons are basically non-bonding electron. It is free, lone pair. Now out of these 4, 1 pair is donated to this hydrogen, because for bond formation between oxygen and hydrogen, we know 2 electrons are required. Okay. Now both these electrons are donated by oxygen. So that is why this is example of coordinate bond, and this is actually H3O plus, which is known as hydronium ion. The combining atom which donates the pair of electron, that is called donor atom, and the other one which is accepting, that is acceptor atom. But don't think it is cation and anion. There is no such thing. The bond is shown by arrows starting from the donor atom to pointing towards the acceptor atom, which you can see in this example. You can also draw it in hydronium ion, but it is not always, it is not any rule. We do not follow it always, but in some examples you can see this arrow sign. And this type of bond, it has special significance in coordination compounds, which is basically the transition compounds of transition elements. There is a separate unit for this type of compounds because their chemistry is versatile, different. So it is not included here. But remember, for coordination compounds, these type of bonds are very important, and that is why these bonds are so important. See, the compounds itself, we are calling this type of compounds as coordination compounds, because in these compounds coordinate bond plays a major role. So that is why we call this type of compounds of D block elements as coordination compounds, where the donor atom we call it ligand, and the acceptor atom we call central metal atom or ion. So if the central metal is neutral, you can call it atom, and if it is carrying positive charge, then we will call it ion. Okay. Some more examples of this coordinate bond or dative bond here we will see. Now this example is very interesting. Here we have ammonia molecule and hydrochloric acid. You can see all these electrons, because the nitrogen electrons are basically in black color. Let me use another color here. So these black colored electrons are basically from nitrogen, and nitrogen, it has total 5 valence electron. You can see total 5 black dots surrounding nitrogen. Now out of these 5, only 3 used up for bond formation with hydrogen, and the electron of hydrogen, that is in red color. So this is ammonia. Now there is a lone pair, so this is not part of any bond, it is non-bonding. Now this lone pair, what will happen? It will capture this H. Now HCl, you can think it as if it is in the form of H plus and Cl minus. We know HCl we can write in this form. Okay, so as if it is H plus cation and Cl minus Nr. Now it is a same type of reaction as you have seen in the previous example, where water molecule is attacking proton. So in this case, as if ammonia is attacking H plus. So see, this is the newly generated bond between nitrogen and hydrogen, where both the electrons in black color, that means both the electrons are coming from nitrogen. So both of these binding electrons came from nitrogen atom, and there is a positive sign, overall positive sign. You can also put the positive sign over nitrogen because nitrogen is giving both the electrons, so that is why there is a positive sign. Okay, so overall this molecule, how we write it? We write it as NH4 plus. Okay, which is basically ammonia ion, ammonium ion, not ammonia ion, ammonium ion, and Cl minus, that we write as counter ion. Now this molecule, obviously we are discussing this example because now our purpose is to know what is coordinate bond. But in general, if you see this molecule that is formed, which is basically NH4Cl, the product here is NH4Cl, but NH4Cl, as it is ionic compound, so you can also write it as NH4 plus Cl minus. But overall, it is a compound ammonium chloride, which is written in this way. In detail, if you draw the bonding, it will be like this, as it is shown here. But the interesting thing here, this molecule is a very good example of a molecule where covalent bond, ionic bond, coordinate bond, all these three types of bonds are present, and that is why this is very good example. If in exam it is asked, suppose 3 to 4 molecules are given as options, and it is asked that among this molecule, which you choose that molecule where all these three types of bonds are present. So obviously NH4Cl, if present in option, you have to choose that. It is a very good example of a compound where all these three types of bonds are present. Now, if we have already seen what is coordinate bond here. This is the coordinate bond, right? But see, where is the covalent bond? Basically, covalent bond is already present between N and H. 3 covalent bonds are present, which is also present after the reaction. So these 3 are covalent bond. And where is the ionic bond? Ionic bond, what we know, it is interaction between a cation. So this is our cation, and interaction between cation and anion. So this is anion. Okay, so these are the 3 examples of all these types of bonds. Another molecule you will see, you know, this is nitric acid. We write it as HNO3, but in detail, if you write the bonding, it will be something like this. So in this case, where is the coordinate bond present? So here central atom is nitrogen, and you know nitrogen has 5 valence electrons. Now out of these 5 valence electron, nitrogen is using 3 electrons for bond formation with, see, in this bond it is using 1 electron. Second electron used here. Here we have a double bond, so another electron is also required. Now out of 5, 3 used up, 2 remaining. Now the 2 electrons are present in this bond. So this bond between N and O, that is actually the coordinate bond. I can also write the molecule like this, so that you can differentiate between covalent bond and coordinate bond. So I will now use arrow, and there is oxygen. So when you are using arrow, you don't have to put any positive or negative sign, because it already indicates, as you have given arrow sign, it already indicates that nitrogen is positively charged, oxygen negatively charged, because oxygen is not giving any electrons, rather it is accepting electrons. So that is why there is negative charge, but nitrogen is giving electron. Okay, normally what we expect, that a bond, 1 electron should be from oxygen, another one should be from nitrogen, but in this case both are coming from nitrogen. So that is why this type of arrow sign we can give, or it is, or you can write it as the positive charge on nitrogen or negative charge on oxygen, which is in the first picture that is already given in the screen. One more example. So you can recognize this molecule. This is carbon monoxide, carbon and oxygen. Carbon, total number of valence electron 4. Because it is from group 14, consider the last digit. Oxygen is from group 16, consider the last digit, valence electron 6. So here the electrons of oxygen that are in dot, and carbon electrons that are with cross sign. Now basically here those 6 valence electrons, but here all the electrons are considered. That is total number of electrons are given in this picture, so that is why you can have some confusion. But basically these 2 electrons as if it is 1:2, so don't consider it. So don't consider these 2, just consider the 6 electrons that are left. Don't consider these 2, because here the whole that is all the electrons are given. So without looking at these electrons that I have just given a cross mark, if you see the other, carbon is having total 4 electrons, and the 3 bonds that are present between carbon monoxide, 3 bonds. These 3 bonds, out of these 3 bonds, 2 bonds are basically covalent bond. Okay, so here, though here don't think this is a bond. Basically, okay, this picture is confusing. Let me show separately. So here the electrons that are coming from carbon, 2 electrons here, which is non-bonding electron, carbon is not using. Now the 3 bonds that you are seeing here, out of these 3, the first one, that is covalent, so 1 electron given by carbon, second one is also covalent, but the third one is actually coordinate bond. So the electrons that are coming from oxygen, I am drawing it with the blue color. So oxygen is using both electrons in this bond, and other 2 bonds that are normal covalent bond. Okay, last bond is coordinate bond. And oxygen, how many electrons are left? Total 6 valence electrons. It has already used 4, so 1 will be remaining, like this. So you can also draw it as if it is, these 2 are normal covalent bond, and the third one you can draw it like with an arrow sign, and there are non-bonding electrons already present. Okay, this picture, it is also written sometime as there is negative charge over oxygen, and over oxygen there is positive charge, because you have already seen in case of nitric acid that in coordinate bond, when it is drawn as nitrogen, that is donor atom, you can put some positive sign or negative sign. Okay, so different way we can represent, and you should know all these, because in some books you may find this type of example, maybe in other books there will be different representation. So don't be confused, they are actually all same. Now we have discussed ionic bond, covalent bond, coordinate bond. Now we have reached another type of bond, which is hydrogen bond. Now this is not actually, we cannot say it is a fully formed bond that you have already seen in case of covalent bond, ionic bond, and coordinate bond. This is not like that. It is as if an interaction, but still we call it bond, because this interaction is very significant. Now why it is hydrogen bond? Obviously hydrogen atom is in. Otherwise why we'll call it hydrogen bond? The force of attraction existing between hydrogen atom. Now which hydrogen atom? It is not that any hydrogen atom capable of hydrogen bond formation. No, it's not like that. So it is possible only when the hydrogen atom, which is covalently bonded to a highly electronegative, and not just any highly electronegative, it should also be very small in size. Okay, so bonded to a highly electronegative and small atom, and similar atom of another covalent molecule. Now if it is you think it is a little confusing, when we'll see the example it will be clear. So very good example of hydrogen bonding is water molecule. Now here you can see total 3 water molecules are present. This is 1 water molecule, this is 2nd water molecule, and this is the 3rd water molecule. And the dotted sign that you are seeing between these 3 water molecule, that sign is actually the hydrogen bond. Now let me erase all this so that you can see it properly. Okay, so there are some del sign that you can see. Now what this means actually? When we write any fully positive charge or fully negative charge, suppose take the example of sodium chloride, Na plus Cl minus, it is fully developed positive charge. We are not using any del sign. But when it is not fully developed positive charge, suppose it is partial positive charge or partial negative charge, then to differentiate between fully developed charge and partially developed charge, we use this type of del sign. Between hydrogen and oxygen, obviously oxygen is more electronegative, and that is why more electrons, 2 electrons are involved here, but these 2 electrons, because of oxygen's higher electronegativity compared to hydrogen, these 2 electrons, it will be close to oxygen, like this. Let me draw it. So both are as if close to oxygen, though it is covalent bond, but still because of high electronegativity of oxygen, both the electrons are close to oxygen. So that is why there is partial negative charge, which is drawn here with a del sign, and partial positive charge over hydrogen, because electrons are going far from it. So as a result, what is happening, some polarity is generated, though I am not saying H and O bond is broken, it is H plus and O minus. No, it is not that. There is still bond present, but it is partial charge development. So that is why there is a negative sign. And also there is a positive del plus to another H. Now what will happen, as this hydrogen is slightly electron deficient because of this type of polarization, and consider another oxygen of the second water molecule, there is negative charge partial. So that is why now there will be some interaction between this partial del plus, this is plus, all these are plus, and del minus of oxygen. Okay, and see, now try to look at the definition. What it is saying, it is saying that hydrogen atom which is covalently bonded to highly electronegative atom. So just take this H, it is attached to oxygen, highly electronegative and small also, and it is also attached to similar atom of another covalent molecule. That means it is attached to similar atom. Similar means oxygen of another water molecule. So that is why the definition is like this. And see, only 3 elements are capable of hydrogen bond formation. That is, I mean to say, when hydrogen is attached to these 3 elements, because only these 3 elements can fulfill the criteria of high electronegativity and small size. So what are those 3 elements? It is F, oxygen and N. So only these 3 electrons, you will see there is hydrogen bond formation possibility is there. Now don't think that that is any oxygen hydrogen containing compound there will be hydrogen bond. No, it is not that. This condition must be fulfilled. That is, H is directly attached to this type of electronegative atom, and it is suitably oriented to the similar atom of second molecule. Then only hydrogen bond formation possible. So here this bond, which is solid bond, this is actually covalent bond, but the dotted line, basically hydrogen bonds are shown with dotted line, so that you can differentiate between actual covalent bond and what is hydrogen bond. So that is why dotted signs are used. Hydrogen bond is possible mostly in polar covalent molecule. Now water is polar covalent. What is polar covalent? You know, covalent bond, when it is present in any molecule, you can call it covalent molecule. Now water is also covalent molecule, but because of this electronegativity difference between oxygen and hydrogen, there is some partial polarity character generated. So that is why it is called, it is not purely covalent. It is actually covalent, but because of this type of polarity generation, it is actually polar covalent molecule, where partial charge separation is present. So only in this type of molecules hydrogen bond formation is possible. As this bond existed between partial charges, that is the reason it is considered to be weak bond than ionic and covalent bond. So don't think that it will be as strong as covalent or ionic bond. Obviously ionic and covalent bonds are stronger compared to hydrogen. And here no such electron sharing is also present, as you know in case of covalent. And also like ionic bond, what you have seen, just take this example of Na plus Cl minus, fully developed positive charge, fully developed negative charge. So that is why the interaction between these two is so strong. It is so strong that they form crystal, which is, to break crystal we have to provide so much energy. Hydrogen bond is not like that. It is weaker, obviously, but still it is significant, because when there is hydrogen bond present in any molecule, it has tremendous effect on its property. Okay. The physical state of a compound can determine the strength of a hydrogen bond. So suppose the hydrogen bond is present in any solid compound, and it is also present in another gaseous molecule. Obviously, when it is in solid state, it will be very strong. And the reason is very easy to understand, because in solid state, the molecules are close to each other. So obviously, the interaction will be strong. But in gaseous state, they are far from each other. So hydrogen bonding will be very weak. So in what physical state the molecule is actually present, obviously that can determine the strength of hydrogen bond. So just you can also take the hydrogen, if it is gaseous, water molecule, if it is gaseous form, that is vapor basically, then hydrogen bond will be very weak. But if you consider solid state, then it will be strong. Here we have two examples. This is organic compound. One is orthonitrophenol, that is the nitro group and OH group, they are at ortho position, that is 1 position and 2 position. But in the second one, same molecule, it is actually isomer, only the position is different. Suppose now it is at okay, I am putting 2, this is 1, this is 4 position, that is para position. Okay, so para nitrophenol and orthonitrophenol, why we have taken these two examples? Look at the first molecule. Here the hydrogen bonding that you are seeing, it is between this H, which is attached to oxygen, and it is also having some interaction. This dot sign is basically hydrogen bonding with oxygen atom. Now this oxygen atom is not of any other molecule, it is already present in the same molecule. Okay, so that is why this type of hydrogen bonding we call intra. Look at the spelling, INTRA. And when it is present between two individual molecules, that is the second picture. Now the term is inter, INTER. So intra means within same molecule, inter means at least two molecules must be there. Now the position of OH group, it is not close to anything. So you cannot expect any intra molecule. But the oxygen, this hydrogen is attached to oxygen. This hydrogen can be close to the oxygen of NO2 group of the second nitrophenol molecule. Now hydrogen bonding is possible. So though in both molecules hydrogen bonding is there, but one is intra, another one is inter. And this type of inter and intra, that is depending on whether intra is present or inter is present, it has direct effect on the physical property. Because when it is intramolecular, you can see it is already satisfied with hydrogen bond formation within the same molecule. So this hydrogen, it will not make any hydrogen bonding with second molecule. As a result, what will happen? Hydrogen bonding will not be present between two individual orthonitrophenol. So you can easily separate them. So you can expect their boiling point will be less compared to inter. Because in case of second one, you have to break all these interaction. You are just seeing here two para-nitrophenol, but this type of as if you can consider this chain is continuing in the left hand side and also in the right hand side. Then several para-nitrophenol will be connected to each other through this intermolecular hydrogen bonding, and you have to, when you are converting from liquid to boiling state, you have to break all these hydrogen bond. And to break all these hydrogen bond, you have to provide energy. So now making some gap between these molecules, that is, you are converting from liquid to gaseous state, you have to provide more energy because you are now breaking all this hydrogen bond. So in this way you can understand when there is intermolecular hydrogen bonding present, boiling point will be high. So based on the type of interaction, it is classified into two types. It may be intermolecular or intra. Now if you consider this example, that is the first example that we have seen, here also it is example of inter, not intra. Hydrogen bonding related problem. Intermolecular hydrogen bonds are not present in what? Not present. That means rest of the 3 molecule, there will be presence of intermolecular hydrogen bond. Inter, it is not intra, so it will be between 2 individual molecules. Now the first molecule, it is actually alcohol, and here the hydrogen is directly attached to electronegative atom. Now it can make interaction with the oxygen of the second alcohol molecule. So second alcohol molecule I am drawing. This is basically CH2CH2H, ethanol or ethyl alcohol. So this type of interaction is possible. So this is not correct answer. Now come to the second one. Basically you don't have to draw the picture. I'm just drawing it so that you can understand better. You just have to check whether the hydrogen atom, it is directly attached to the electronegative atom like oxygen or nitrogen or fluorine. If it is directly attached, then only they will be capable forming hydrogen bond. Second one also, it is acetic acid, carboxylic acid is present. This H is directly attached to oxygen. The third one, H is directly attached to nitrogen. So all these 3 can form hydrogen bond. But the last one, this is basically ether. If I draw the structure, full structure, it will be like this. Now see, hydrogen is attached to carbon. It is not attached directly to oxygen. So it cannot form intermolecular hydrogen bond. So that is why this should be the correct option, dimethyl ether. Second question, which among the following will not form intramolecular hydrogen bond? Now it is asking which one will not form intra. Now all these 4 molecules, one thing is common, and that is all these compounds, there is 1,2 substitution. That is ortho substitution. Okay. Now don't think that when it is ortho, it is capable of intra. No, it is not that. You just have to check whether hydrogen is directly attached to electronegative atom or not. So in the first case, CO2H and OH group present at 1 and 2 position. Now if I draw the molecule like this, COH and then C double bond O and oxygen and then H. Now see, it is suitably positioned in such a way that this oxygen is very close to this hydrogen. You can also consider this one. I have here taken the C carbonyl oxygen. So this type of interaction is possible. So this is not correct option. Now come to this one. Here also this H, it can directly interact with the OMe group present at ortho position. Come to this one. Here this H is directly attached to oxygen. And if I write the NO2 group in this way so that you can understand. So here also H is close to the second oxygen. Interaction is possible. But this one here again you can compare it as if it is like this ether example, because this is also ether. So if I write it, it is O then CH3. So hydrogen is attached to carbon. It is not attached to oxygen. So how it will form intramolecular hydrogen bond? Okay. So this option, that is option 2, should be the correct option. Now another term, that is next topic, is bond parameter. What is bond parameters? Now obviously, as the term suggests, there will be some parameters that will directly control bond. Okay, because this chapter is all about bonding, so we have to know what are the factors which directly affects chemical bonding. So bond parameters in general, if we see the definition, it refers to the characterization of covalent bond on the basis of different types of parameters. These bond parameters, why they are important? Because they can give you some insight into the stability of a chemical compound. So if you know these parameters properly, you can have clear idea about the nature of the bond or whether it is stable. Okay, and also the strength of the bond. So all these things will be revealed to us if we know these parameters properly. Fine. So what are those parameters? So these are the parameters: bond length, bond order, bond enthalpy, or sometimes it is also called energy. What is difference between enthalpy and energy? In the last class, I have mentioned it clearly when we have discussed lattice enthalpy and lattice energy. Okay, basically enthalpy energy both are having energy unit, but there is a subtle difference. Fine. Then bond angle, resonance, and polarity of bonds. So all these 6 factors, one by one, we will discuss. The first one is bond length. Okay. Number 1, bond length. Now you can understand what is bond length. Obviously, it is the length of the bond that is present between two atoms. But if we want to give actual definition, it will be like this: the bond length refers to the distance between the centers of the nuclei of the two bonded atoms, and it is at equilibrium position. Equilibrium position, this condition must be mentioned properly, because their position, it may not be fixed, because they are always vibrating. It is not they are sticking to each other. It is fixed position. They are always vibrating. Their position may be changed, but it is when they are in equilibrium position, then only you can apply this definition, that it is the distance between the center of the nuclei of two bonded atoms. So here we have bond between atom A and atom B. Atom A is slightly smaller in size, but this is the nuclei. This is the nuclei, and this is the radius of the first atom. This is the radius of the second atom. If you add these two, that is the distance between the center, it will give you the bonding. And it is approximately, not exactly, but we have to take at least some value. So for the sake of our convenience, it is approximately equal to the sum of the covalent radii of the two bonded atoms. So covalent radii is basically, if I ask what is the covalent radii of A, this is the covalent radii of B. This is the covalent radii of B. So when you take the sum, that will give you, that is Ra plus Rb, that is actually the bond length. So bond length is basically capital R, which is Ra plus Rb. The stronger the force of attraction in between the bonding atoms, the smaller is the length of bond. Okay, so depending on the, that is bond length, suppose you have two different compound of AB. In one compound, the distance between AB, there is a fixed value. Another compound, the distance between AB, there is another value. So if you compare these two, obviously when the length is smaller, you can say it will be stronger compared to the other. And also increase in number of bonds. That is, if it is multiple bond, suppose you have bond between A and B, this is single bond. Another case may also arise, there is double bond between A and B, or it may be triple bond. Though it is true that all the atoms cannot form 3 or 2 bonds, but when it is possible, just compare these three. Number of bonds are increasing from 1 to 2 to 3. So when there is increase in number of bonds, that is, I'm talking about multiple bonds, obviously there will be decrease in bond length. That means here all these 3 bonds are basically bond between A and B, but difference is multiplicity. So these bond will be having lowest bond length. Higher is the number, lesser is the, that is lower is the length. Okay, so A triple bond B, that will be having minimum bond length. Then next will come A double bond B, and A single bond B, that will be having maximum bond length. Okay, now with proper example you can understand it. See, here we have CC single bond, CC double bond, and CC triple bond. This is triple. Now this is gradually decreasing, 154 picometer, then 133 picometer, 120. So this is a very clear example where you can understand the last statement in the previous slide. Fine. Here we also have some other examples: HO, HBr, HN. Fine. See, H2 is very small because both the atoms are very small in size. And we also have N double bond N, C, basically it is triple bond, N triple bond N. Then chlorine atom, bromine, all these are basically diatomic molecules, chlorine, bromine, argon. So here you can see it is from chlorine to, when you go to bromine, size of the atoms increases. So 199, this is 2 to 8. This is 267, so it is increasing, which is as expected. Also you can see when you are moving from HCl to HBr, H this side is fixed but Cl is changing to Br, so obviously there will be effect in the size, which is clear here. Fine. Now come to this table. Here we have some molecules. The bonded, that is, these are the molecules. In the next column, which bond we are considering, that is mentioned. Because if you consider HCHO, formaldehyde, there is carbon hydrogen bond, there is also HO bond, but we are just focusing on this bond. So that is why which bond we are focusing, that is mentioned in the next column. Then come to the next column, bond order. What is bond order? Now this is the second parameter we are going to discuss. This is basically number of shared pair of electrons between bonded atoms. So here shared pair of electrons. Now we know when there is a single bond present, that means one pair, two electrons are involved. If it is two bonds, then two pair, right? So bond order is basically number of shared pair of electrons between bonded atoms, or directly simply you can say it is basically how many bonds are present. That is the bond order. So if you consider H2 molecule, bond order is 1, that is single bond present. Oxygen molecule, 2 bonds are present, so bond order 2. Bond order 3, 3, then 2, 1, 2. Very simple. Fine. So now you know what is bond order. Some more informations. The number of bonds formed between two bonded atoms in a molecule, that is the bond order. Very simple. If the bond order of a covalent bond is 0, that means there is no bond. So the two atoms in question, they are not covalently bonded. No bond exists. Fine. So at least it must have value 1. Otherwise, how there is some bond? Stability of molecules increases with increase in bond order. If bond order is very high, obviously stability high. Just take the example of nitrogen. We know nitrogen is very stable molecule, almost inert. Now the reason behind it is that if you want nitrogen to take part in any reaction, you have to break these bonds. Individual nitrogen atom if you want to get. And to break this bond is really difficult. Okay? Because breaking 3 bonds, it requires more energy. So that is why stability is also high, and that is why this statement is given here. The stability is directly related to how many bonds are present, or you can say it increases with increase in bond order. Next point, isoelectronic molecules. That is, if you have some molecules, or it not necessarily molecule, it may be ion also. Isoelectronic molecules and ions, they will have same bond order. So when you have any species having total number of electrons same, that is the definition of isoelectronic, then you will see they will have same bond order. So here we have these two examples, carbon oxygen, nitrogen oxygen plus. Carbon monoxide is the first molecule. Second molecule is it is not nitric oxide, but it is positively charged nitric oxide. Okay, 1 electron less. Now in carbon and oxygen, carbon is having total valence. Okay, you can also count the total electrons. 6 electrons. Oxygen is 8. That is atomic number of bonds considering. So it is total 14 electrons. Then come to NO plus. Nitrogen total electrons 7. Atomic number 7. Oxygen is 8. 8 plus 7 is 15, but there is a positive sign. So 15 minus 1, it is 14. So again, you are getting same number. So that is why these two are isoelectronic species, and bond order for both is 3. Next point, with increase in bond order, bond length decreases. So very important relationship is bond order, that is BO, that is inversely related to bond length. Never forget this, because whenever bond order is high, just take this example, CC single bond, bond order 1, CC double bond, bond order 2, CC triple bond, bond order 3. So length is decreasing as bond order is increasing. So these two are inversely related to each other. Stability is directly related to bond order. Bond order increases, stability increases. But when you consider bond length, it is inverse relationship. Okay. Which of the following have identical bond order? So this is basically multiple correct choice. That is, out of these 4, at least 2 you have to choose. Okay. So this is multiple correct choice. Fine. Now, as I have mentioned in the previous slide, just you have seen that isoelectronic molecules or ions will have same bond order. Now it is asking in which case identical bond order present. So for these ions, basically all these are ions, there is some negative charge or positive charge. If you count the total number of electrons, just we have done for the last example, that is carbon monoxide and NO plus, same thing you can also do here. So Cn minus NO plus, then O2 minus and O2 2 minus. Different types of ions are there. O2 minus is superoxide, O2 2 minus is peroxide. So C and N, that is 6 for carbon, 7 for nitrogen, 6 plus 7, 1 more electron for the negative charge, it is 14. And for NO plus, we already knew it is 14. So these two are basically isoelectronic. So these two should be correct. But what about the other two? O2, 2 oxygen atoms, that means 8 plus 8. But there is a negative sign. So it should be 8 plus 8 plus 1. And for O2 2 minus, it is 1 extra compared to C. Here Cn minus 14, 6 for carbon, then for nitrogen, and this is for the negative charge. Then for N it is 7, 8 is for oxygen, minus 1 because there is a positive sign. Come to O2 minus superoxide, it is 8, 8, 1 electron extra, 17, and the last one, it is just like the previous one, only difference, and you have 2 extra electron. So these two are not isoelectronic, but the first two are isoelectronic. So that is why these should be having identical bond order. Next problem, the correct order of increasing carbon-oxygen bond length in these 3 species. We have 2 neutral molecules. One is carbon monoxide, another one is carbon dioxide, 2 different oxide of carbon. We also have anion, CO3 2-, which is basically carbonate anion. But the thing is, in all these 3 species, you will have carbon-oxygen bond. So we have to answer increasing CO bond length. So you can see different orders are given. So just take the option A. What it means? CO is having maximum carbon-oxygen bond length, then in CO2, then carbonate. But which option is correct? Now, if you know the bond order of CO bond in these 3 molecules or ion, you can directly answer the question, because bond order, it is inversely proportional to bond length, and we have to answer related to bond length. So just focus on bond order. Try to find out what is bond order, okay, of these 3 species. So had the bond order, the shorter is the bond length, that we already know. Now for CO, we have discussed this example. Remember, in coordinate bond, where we have already seen that there is 3 bonds present between them. So its bond order is 3. Then what about carbonate anion? Carbonate anion, if you draw, it is C double bond O, then 2 oxygen carbon single bond. Okay. Now how you will understand that what is the bond order? Because there are 2 different types of bond. C double bond O is present, C single bond O is present. Okay. So this is basically polyatomic ion, and for polyatomic ion, there is a specific rule you can use if you want to calculate the bond order, and that is total number of bonds. So here total number of bonds 4 divided by total number of position. What I mean by position is basically how many okay, let me use different color. By position I am trying to say, so this is one position, this is another position, this is, don't think this is 2 positions, but both the bonds are together. So this is a single position. So total position 3, total number of bonds divided by total positions. So it will give you 1.33. So this is the bond order. In this way you can calculate it for polyatomic ions. So see, when we will discuss resonance, it will be more clear to you. So though it is in this picture, as I have drawn CO3, it seems as if there is single bond and there is also double bond, but we have to take the average. We have to consider the other resonance structure. When we will discuss resonance, it will be clear to you. Right now, just apply this formula, total number of bonds divided by number of positions, and it will give you 1.33. And what about CO2? Now for CO2 it is easy to understand because we know CO2 is this molecule, this type of, and both the bonds are 2. So obviously bond order is 2. And now we know the bond order. If you see maximum bond order, that is for CO. So bond order of bond order is CO, then CO2, and then carbonate. But we have to consider bond length, not order. So now you have to reverse it. CO3 will come first, CO3 minus, then CO2, and then CO. So this is how CO looks. See here, these blue electrons are basically coming from oxygen. This is covalent bond, this is covalent bond. The third one is not covalent bond. This is coordinate bond, which is shown with the arrow in the second picture. So here bond order is 3. But correct option will be this one, that is the reverse order. Maximum bond length, that will be in that case where bond order is minimum, and bond order is minimum for carbonate. So that is, it will come first, then CO2, and then CO. Okay, so we will end here. Only 2 parameters we have discussed, bond length and bond order. Rest of the parameters we'll discuss in the next class. Thank you for listening.